Everyone, we're back again, and we're now talking about trying to find the ages of rocks. And this is something geologists try to do all the time. We're going to do a lot of different techniques, but the first technique, we kind of have to talk a little bit about chemistry.
I like chemistry. Works for me, works for a lot of things, and one of the things that it works for is why we have radiation.
So what radiation is when an atom that is not stable decays. What I mean by decay is it emits something. There's alpha decay, there's beta decay, there's gamma decay. In all those, they're slightly different. Like alpha emits a helium particle, a beta decay is a loss of an electron, and gamma decay is really just emitting light. So we've got three different ways that an atom can change, and let's first talk about what an atom is made of.
All right, this atom in particular is an electron cloud model, and what we see here is you have electrons circling a nucleus that's composed of protons and neutrons.
And what do we know about protons and neutrons?
We know that protons are positive, and we know that neutrons are neutral. The electrons going around the outside are negative. The thing to understand about atoms in the case of radioactivity is the number of protons dictate what an element actually is. So if you change the number of protons,
then you're going to change what atom you have.
That's correct.
Like if we look at the periodic table tells us exactly how many protons are in each element. So if you're talking about carbon, we've got
6 protons.
If we have oxygen,
we have 8 protons.
Looking at the periodic table, just looking at the atomic number tells us how many protons there are. Typically, there would be the same number of neutrons to make up the mass of the element, but that's not always the case. Some atoms are heavier because of the extra weight of those neutrons. And if it's a neutral atom, how many electrons are flying around?
Well, your positives and negatives have to balance, so that means the same number of electrons. So in the case of oxygen,
8 electrons. In the case of carbon,
6 electrons.
There we go. So that's the basic atomic structure that we really need to know. What happens in radioactive decay is the fact that this unstable element, like carbon-14 or uranium-238, or there's an entire list that you can go through to look at radioactive elements, they are unstable because of either having too many neutrons or there's just too much energy internally for the atom. So the way they can release that energy is by, like we said, emitting something. An alpha particle, a beta particle, or a gamma particle. So here we've got the old bucket of atoms, and if I add some atoms to our sample, I've got 30 carbon atoms here. And I'm just going to let the simulation run, and you can kind of see what happens. What are you observing?
Well, what I'm seeing is carbon is changing to nitrogen.
So the unstable carbon-14 is turning into a more stable nitrogen-14.
Right, and nitrogen is stable and it doesn't decay any further, and so we can make a comparison.
So what we want to do, if I rerun that and reset it, every so often, if I start off with 30 carbon atoms, I lost so many by a particular point. If I started with 30, I would end up with 15 that we call the half-life.
So by definition, a half-life is the time it takes for a radioactive element to decay.
To
halfway.
Half of its original.
That's right.
So if we started here, we started with 30 carbon atoms, and when we hit that one half-life, we now have 14 carbon atoms and 14 nitrogen atoms. But if we wait that same amount of time again, we're going to get to a second half-life. What happens at the second half-life?
Well, you'd think that what would happen was exactly the same amount of atoms would decay, but it doesn't work out that way. They take half of what's left of the carbon.
I had 15 left after the first half-life. That means we look at those 15 carbon atoms, and after one more half-life, half of those have decayed. So now we're around 7.5 carbon atoms. You can't really have a half of a carbon atom, but you get the point.
Mm-hmm.
If we wait a third half-life, then half of the 7.5 will decay into something else. It's half of what remains at each moment.
Now, technically, you would think that that would mean you could go on forever and ever. But there's a point at which they can't be measured anymore. You can't just take some carbon-14 and infinitely count down and always have a half, a half, a half, a half. There is a point where you can no longer measure it with our current technology.
So carbon has a half-life, and if we actually measure out the rate at which it decays, it's around a little over 5,000 years. So if I add atoms again to my setup, and I let the setup run, when we get to around that 6,000 year mark, you can see that half of the carbon has now turned into nitrogen. If we wait up until around that 12,000 year mark, we've hit half of the half. So that means that now another, if we started at 100% carbon, we went to 50%, then we went down to 25%, then we'll go down to 12.5%, and we keep losing half of what we originally had each half-life. And eventually, like you said, all carbon-14 will turn into nitrogen-14. Well, what's the difference between carbon and, say, uranium?
It's the length of the half-life.
So the big difference here, when I switch over to uranium, you're going to see the same trend. I'm going to throw a bunch of uranium atoms here. Uranium decays into lead, and the same trend occurs. The same graph shape occurs between the amount of uranium left and the amount of lead that is created.
Now, one of these axes are a little different.
Which one's that?
Well, I'm noticing that now we're looking at billions of years instead of thousands of years.
So for uranium to decay, if I had 100 grams of uranium, for it to decay into 50 grams of uranium and 50 grams of lead, I'd have to wait around 4.5 billion years, which is kind of as long as the Earth's been here.
Yes.
Interesting. Another 4.5 billion years would be when I could finally get down to 25% of the uranium left, and 75% of it would be lead. And this is what allows us to kind of rewind the clock. When we look at a sample and we see the ratio of, say, uranium to lead or carbon to nitrogen, we can then kind of work back along this curve and work back the math to figure out when the sample was at 100% of the unstable element, which will help us find the age. So let's do one example problem here. The example we came up with was that a sample contains about 100 grams of this acetane element, and when we measure it again, the sample now has 12.5 grams of the acetane. And if the half-life of acetane is 8 hours, well, how old is this sample?
Well, the easiest way to do this is to figure out how many half-lives you have. If you know the number of half-lives, you just take that number and multiply it by the length of the half-life. So if we have 2 half-lives, 8 times 2. If we have 4 half-lives, 8 times 4.
So how many half-lives have we got? How do you even know what half-life we're dealing with?
Well, we have a 100-gram sample of acetane, which means to me that if we cut that in half, 1 half-life, we have a 50-gram sample.
Okay, so that would be 8 hours.
That would be 8 hours. But we're not down to the number we need to be down to.
Okay.
And so we now take the 50 and cut it in half again, which is 25 grams of acetane, which is 2 half-lives.
Which gives us 16 hours.
And then if we take it one more time, a third half-life, and cut 25 to 12.5, we now have 3 half-lives.
So 3 half-lives would be this sample is 24 hours old.
24 hours old.
So it's not that you're going to, in 24 hours, just keep losing 50 grams of acetane. You lose half of what remains as the acetane turns into a new sample. Understanding radioactive decay and understanding how a half-life works is going to be really important when we try to figure out the age of things like rocks.
And the things around the rocks.
Sounds good? We'll talk next time.